Good morning. Myself, Dr.D.Raguraman, Assistant Professor, Department of Automobile Engineering at School of Mechanical Engineering, Bharat Institute of Higher Education and Research, Chennai. This video lecture, we are going to see about the topic properties of fluids, which is coming under the course code U18PCAU302, Engineering Fluid Mechanics. So we will see the basic properties of fluids under the fluid mechanics. So before going to see what are the properties of fluids, we will see what is fluid mechanics. Under that, we will see about what is fluid kinematics and fluid dynamics also. Then we will be heading into properties of fluids. And if you're seeing about fluid mechanics is what it is a branch of a science, but that deals with the behavior of the fluids. Fluids means it is either liquid or gases. That's what they call it to be a fluid. It is a rest condition as well as in motion condition. So that's what we are further dividing it as rest condition. If you are seeing the study of fluid at rest condition is what you are calling as a fluid static. And the other case is what if you are considering about the motion, you will be subdividing into two categories: fluid kinematics as well as fluid dynamics. In case of fluid kinematics, the study of fluids in motion where pressure forces are not considered is called fluid kinematics. And the study of fluid in motion where pressure forces are considered is called fluid dynamics. So now, if you are seeing some of the important properties in case of fluid properties we are going to see in this video lecture, that's what density, then specific weight, specific volume, specific gravity, viscosity and compressibility, bulk modulus, surface tension, capillarity, and fluid pressure finally. Then on this video lecture, what we are going to see is, we are going to see up to the viscosity. In viscosity, we are also solving problems in viscosity. So compressibility, bulk modulus and the remaining properties of fluids will be covered on the next video lecture. So if you're seeing first property about upon density, the density is what otherwise it is called to be as a mass density. By defining the density is what it is defined as a ratio of mass of fluid to its volume. If you are considering particular volume, and the particular volume, how much of mass of fluid is occupied, that is what it is meaning with the density. So thus the mass per unit volume is what we are calling as a density. So it is denoted by the symbol rho, and the unit of mass density in SI unit is what a kilogram per cubic meter. That is what kg per m cube. It is what a kilogram per meter cube. So mathematically, if you are seeing density is what it is defined as mass divided by volume. That is rho equal to m by v. That is what rho equal to mass of fluid divided by volume of fluid. That's what we are saying mathematically, rho equal to m by v. And here rho is what density, and m is what the mass, and v is the volume. If you are seeing the density of liquids, that may be considered as a constant. For a case of a liquid, it is constant because fluid we had already seen it is a liquid as well as gases. Under the fluid, in case of a liquid, it is constant. But if you are seeing the gas, it will be changing with the variation of pressure and temperature. Because if you are seeing the difference between a liquid as well as gas, there is importantly one difference is there: a compressible fluid and incompressible fluid. Which can be able to compress is what gases, it is can be said than a compressible fluid, but incompressible is what liquid. So that it's depending upon that you will be having the density is being getting constant for the liquids, and gas it will be varying with respect to pressure and temperature because it is a compressible one. And that's what a density of water, that is what a density of standard liquid means, that is density of water. So density of water is said to be 1000 kilogram per meter cube. If it is per centimeter cube means it will be a 1 gram. So that's what you will be able to understand about this density within a different emerging, because based upon the density value, the red colored one is what the substance will get floating whenever it is not crossing the density of water. If it is crossing the density of water value of this 1 gram per centimeter cube, then it will be completely going to get immersed. So up to that it will get floating, and that's what here you can able to see here you are having 0.1 gram per centimeter cube for the substance, and we will be knowing water density is being 1 gram per centimeter cube. That is what 1000 kilogram per meter cube. So by that way, you can able to see it is having only this much amount of merging is there, okay, in the water. So it is not going to sink in the water. So if your density of a substance is being less than that of a water density, then that substance is going to get float. So this is what in the next module you will be having the another topic, buoyancy also you will be seeing, and hydrostatic forces you are going to see. That's what on the continuation module you will be seeing. So that is what it is interconnected with other properties also. So that's why density is being an important property whenever you are comparing for the case of on a solid as well as for the fluid. And still you can able to see it for a different type of a fluid. You can be able to see a layer of fluid, a 7 layer of fluid. It is being popular. So you can able to see here a 7 layer of density column. So you can able to see a different density for a different fluid. As per of we know water is having what, it's having a standard density of 1000 kg per meter cube. That is what in case of gram per centimeter cube means 1 gram per centimeter cube. So that's what water. So less than the water density is what vegetable oil as well as alcohol as well as lamp oil, and more density than that of water is what damp dish soap solution and corn syrup and honey. These are all having more density. So depending upon this density of an fluid property, liquid property, you will be having a floating of an solid object. See the solid object, the ping pong ball, it is having a very less density value, and also the bottle cap. Then crepe tomato is comparatively high density than that of slightly less than that of an corn syrup, and that's what it is having slightly higher than that of water, so that it is getting crashing that of water. But ping pong ball is what a very less density, so that it is floating even in a very less density fluid lamp oil. So but screw, metal screw, we are seeing its density is being more 7 gram per centimeter cube. So even it will be going to get sink in case of honey, which is having a more amount of density compared to all the fluids. So that's what a better understanding you will be getting in case of a 7 layer of density column about the density. So this is what a illustration of the same thing. So you can be able to see it is getting a sinking, and the pink ball is getting floating. Okay, the pink ball is going to get floating. So that's what about of a density. The next property is specific weight or weight density. The specific weight or weight density of a fluid is the ratio between the weight of a fluid to its volume. So the weight per unit volume of a fluid is what called to be a weight density, and it is denoted by a symbol W. So the small w, that is equal to weight of fluid divided by volume of fluid. So weight of fluid can be identified as a mass of fluid into acceleration due to gravity. So that will be what mass of fluid into acceleration due to gravity can be written as small g. So mathematically you will be writing it small w equal to capital W, that is weight of fluid, divided by capital V is what volume of fluid. So the value of specific weight or weight density for a water is 9.81 into 1000 Newton per meter cube in case of SI unit. So that's what, as we had seen, specific weight definition is being what? The weight per unit volume of fluid. That is what you will be seeing as a weight density. The better example you can able to see in case of our bone joints. So on the joint you will be having a stance and swing. It is because of this fluid property, a specific weight density property. And the next property is being what, a specific volume. So in case of a specific volume, if you are seeing, the specific volume of a fluid is what it is defined as volume of a fluid occupied by a unit mass or a volume per unit mass of a fluid. That is what you will be calling as a specific volume. So mathematically it can be expressed as volume of fluid by mass of fluid. In case of density, what we said, it is mass of fluid per volume of fluid. So that's why it is being a inverse of a density. So the density we had seen the symbol as being rho. So inverse of mass of fluid by volume of fluid means it is what? It is being a inverse of a density. And the next thing is being what, a specific gravity. Otherwise, we can say it as a relative density. So the specific gravity is what it is defined as ratio of weight density of a fluid to the weight density of a standard fluid. So whatever the substance you are going to check for a weight density, that is what a relative density. Why you are saying relative density is we are going to check with the standard. What is the standard? With relation to that, we are checking what might be it weight density. So that's why we will be saying with the other name as relative density. So if you are seeing for the liquid, the standard fluid is what? It is taken as water. And if it is a gas, the standard fluid will be what? It is a air. So for the gas, the standard fluid is taken as air. So that is what it is otherwise called as relative density. So in symbol, it is represented as a capital S. So mathematically, S is what for the case of liquid, weight density of a liquid, what liquid we are going to check for a weight density, that is with respect to the standard liquid is what water. So it is taken with ratio of water. Similarly for the gas, the standard fluid is what air. So in the denominator we will be putting weight density of air. What gas we are going to check, that will be at the denominator, and that denominator we are putting what is the standard fluid. The air is kept at the denominator. So the weight density of a liquid is what? It can be calculated S equal to S into weight density of water will be giving you what is the particular weight density of a liquid. So the density of a liquid means it is S into density of water. So that is what in case of weight density means we are making its standard density for a water is 1000 into G. So that will be giving you what will be the weight density of water. That will be what you will be having the mass. That is 1000 is what this is being what a density of a standard liquid. That is what for the water into G. That rho into G is what a W. That is what weight density of water. So similarly, if you are directly multiplying with the density of water, that is what a density of liquid. So if you know the relative density, you can able to identify what will be the weight density and what will be the density, that you can able to identify. So by this way, relative density means what? With relation to another one, you are identifying. That is what in the case of an air you are having, and in case of a liquid, standard liquid, if you are checking, you will be having the variation of mass. A quartz, if you are seeing, it is having just 0 to 500 gram, but it is going to increase its mass if you are going to check in the case of a water. So by this way, in case of a water, if you are immersing, you can able to check what might be the relative density. So different gemstones and its relative density can be identified with the help of this technique. You will be going to immerse in water on one side, another side will be its standard mass, so that you can able to identify what might be its relative density. And now we will see the problems up to this, then we will head into viscosity. So a simple problem, you are required to calculate a specific weight, density and specific gravity of 1 liter of liquid which weighs 7 Newton. If you see the given data is 1 liter is given, so volume is given. Yeah, 1 liter of water if you are taking, the 1 liter of water is equal to 1 by 1000 meter cube. So from how you are getting is, you know the relation 1 liter equal to 1000 centimeter cube. If you are taking a 10 centimeter cube, on the 10 centimeter cube, you can able to make it as a volume of 1000 centimeter cube. So that 10 centimeter box, it can contain a 1 liter. So from that relation, you will be making 1 liter is 1 by 1000 meter cube. So we had standard relation 1 liter is equal to 1 by 1000 meter cube. So in the question they had given a 1 liter of liquid. So 1 liter equal to 1 by 1000 meter cube. And what is the other data given is weight is 7 Newton. All the other things we can calculate because we have the standard relation. With the help of relation, we can calculate all the things. So specific weight is what? It is weight per volume. So the weight now we are having 7 Newton and the volume also you will be knowing it is 1 by 1000 meter cube. So we are substituting that 7 Newton divided by 1 by 1000 meter cube. So by calculation, we are going to get what is the value of on a specific weight. Similarly, a density, we are knowing density with respect to specific weight, you can able to calculate it, that is being W by G. So that W now only we had calculated, it is being 7000 Newton per meter cube, and G value is what? It is a gravitational acceleration, that is 9.81. So by substituting this, we will be able to identify the density value. So the density value by calculation, you are getting the value as 713.5 kilogram per meter cube. And the specific gravity. as specific gravity is what? It is a relative density. Density of liquid. This liquid is given, okay. So it have a certain weight, okay. So for that particular liquid, what might be the specific gravity? That we are going to calculate with respect to a standard liquid. Standard liquid is being what? Water. So density of liquid by density of water. So density of this liquid we had identified just now as 713.5 kilogram per meter cube. So that divided by standard density of water is what? 1000 kilogram per meter cube. So specific gravity doesn't have a unit because both kilogram per meter cube will get cancelled. So now you are getting the answer as 0.7135. Note that you are not having any unit. So that is what a density of water, that is the standard liquid, that is being 1000 kilogram meter cube. That's what you had substituted and you identified what is the specific gravity of the given liquid. So now the next problem. So in the next problem, they had given a specific gravity of a petrol that is being 0.7. That is capital S value is given. So if the capital S value is given, how to calculate density, we got seen at the last relations. So we can able to identify what is density. Once you are identifying density, you had a correlation with specific weight. So you can identify what might be the specific weight. Okay, so now what is given? 1 liter is given. So again, you are identifying, we know 1 liter equal to 1000 centimeter cube. From that, we will be knowing that is being 1 by 1000 meter cube. Already in the previous problem you got seen. That is what 1 by 1000 meter cube is what? 0.001 meter cube. So specific gravity value, yeah, capital S value is given 0.7. So now density, we know density for a liquid that will be equal to specific gravity into standard density of a liquid. That is what for a water 1000. So S into 1000. That's we got seen in the previous relation. So now if we are substituting 0.7 into 1000, so that you can able to identify it as 700 kilogram per meter cube, because the standard unit for density is what? Kilogram per meter cube. And as the next thing is being calculation of specific weight, we had a relation between density and specific weight. So small w equal to rho into g. So g value we are knowing 9.81 and density just now we calculated 700. So it is 700 into 9.81 Newton per meter cube, so that we can identify it as 6867 Newton per meter cube. And weight value, that is being what? A specific weight equal to weight by volume. Just now we calculated a specific weight, and volume also we are having 0.001 meter cube. So only unknown is being what? Weight. So weight equal to small w into 0.001. So small w value we are knowing it is being 6867. So the capital W value is 6867 into 0.001. So by calculating that, we are identifying what might be the weight of the fluid given. Okay, that is weight of the petrol is being 6.867 Newton. Coming to the next property, viscosity. You're seeing viscosity, we can able to see different liquid having a different viscosity. What is viscosity? Property of viscosity. If you're seeing viscosity, it is a property of fluid that offers resistance to the movement of one layer of fluid over another adjacent layer of the fluid. So layer, if you are seeing for the fluid, it will be having resistance. Inside the fluid itself, you have a lot of layer formation. Even you will be going to see in depth about the fluid properties like boundary layer concept at all on the upcoming modules. So for that viscosity is being important property. So that's what layer by layer, the fluid layers, if you're seeing that layers by layer itself, it will be offering the resistance. That resistance is what you are saying as a viscosity. So the different fluid will be having a different viscosity. Like that of on a density, what you have seen, different fluid having a different density. Like that, the resistance property also you can be able to see for a different fluid, you will be having a different viscosity. A higher density material you got seen honey. If you are seeing a honey, if you are going to pour the honey, you can able to see from the teaspoon while you are pouring honey to any medicine, then you can able to see it is going to take place at a slower rate of flow. But water, if you are pouring, that will go with a high rate of flow. That is what it's having the resistance of movement. That's what you will be meaning with that of a viscosity. So if you are seeing viscosity from the layer to layer, it have an increasing of velocity. What is the resistance? Okay, the resistance is going on decreasing. If it is having more resistant property, then the velocity is going on increasing. So by that way, you can able to increased velocity means that's what the viscosity is dependent upon how much resistance it is going to offer. That's by that way, from the resistant part, if it is going to vary, then you will be having an increasing of velocity. So that is what the top layer will be causing a shear stress on the adjacent lower layer. That's what it's by having a layer by layer. So adjacent lower layer, the top layer is going to cause a shear stress. So that shear stress is what on the adjacent top layer. So this shear stress is what proportional to the rate of change of velocity with respect to y. That is what it is denoted by the symbol tau. So if you're seeing tau is proportional to du by dy, this du by dy is what you are saying as a velocity gradient. So it is proportional to this velocity gradient, and tau equal to mu into du by dy. This mu is what we are saying as a viscosity. So the viscosity value will be tau divided by du by dy. So as I already said, honey, okay, if you are pouring honey, you can able to see how the rate of flow will be, okay. You can able to see it's going with a slower rate of flow. If it is being water, you can imagine it will be going with a high rate of flow. That's what it's the resistance offering by water is very less. But resistance offered by honey, it is being more. So the mu, if you are seeing, as already seen in the previous expressions, mu equal to tau by du by dy. That du is what change in velocity, and the dy is what change of distance, and the tau is what shear stress. We are writing in words shear stress by change of velocity by change of distance. So now shear stress, if you are seeing, shear stress will be what? Force acting on unit area. And similarly, change of velocity means a length per time. That is, you are knowing velocity unit is being what? Meter per second. With respect to time, how the distance is varying, that is what you will be saying change of velocity. And change of distance is, it is what you are having one place to another place, the change of distance, that is being length, okay. So by that, if you are making a simplification, you can identify what might be the unit for the viscosity. So now by simplifying it, you are getting it's force by length square divided by 1 by time. So that is what you will be seeing it, force into time by length square. And we know the standard unit for force and time and length. So force will be what? Newton, and the time will be a second, and the length will be a meter. So that you will be seeing a standard unit being kilogram force second per meter square in case of MKS unit. But SI unit means it will be Newton, force will be Newton. And GKS unit, it is dyne second per centimeter square. But what is very standard in most of the problem, you will be using SI unit only. So SI unit, it is a Newton second per meter square. And the Newton second per meter square, we are having a Pascal, that is for Newton per meter square, we will be using Pascal. So the Newton per meter square, that will be what known as a Pascal, which is represented by PA, that is what shortly Pascal will be written as PA. So SI unit of viscosity, even you can write instead of Newton second per meter square, even you can write Pascal second. And if you are seeing the mu is what? Shear stress and change of velocity, we got seen the unit, okay. So just a repetition of the same thing, okay. So we will be having what we had seen is it is being a Newton second per meter square, that is what Pascal second. So now about the next thing is being what? Kinematic viscosity. The kinematic viscosity, it is being a new symbol, viscosity divided by density. So the viscosity, dynamic viscosity is generally said viscosity. The dynamic viscosity is what? Mu divided by rho is what said to be as a kinematic viscosity. So the kinematic viscosity unit is meter square per second, or it is meter square per second. In CGS unit, kinematic viscosity is also known as Stoke. Thus, one stroke is equal to 1 centimeter square per second. So, if you are converting into a meter, we know 100 centimeter equal to 1 meter. So, instead of centimeter, we are putting 1 by 100, so that we can able to convert into a meter square per second. So, a centistroke, that will be equal to 1 by 100 stroke. Now, considering about types of fluid, we had seen about a viscosity property. Followed by that, it is required to see about types of fluid based upon the viscosity property. There is ideal fluid, a real fluid, a Newtonian fluid, non-Newtonian fluid, and ideal plastic fluids. So, seeing this thing in detail now. So, what is the case of an ideal fluid? So, you can able to see here at bottom ideal fluid. So, you are having a shear stress with respect to velocity gradient. A fluid which is incompressible and is having no viscosity is known as an ideal fluid. So it's have a no viscosity. That's what you can't able to see in a shear stress. Shear stress value is being 0. So if you are having some resistance, then you will be having a shear stress. The shear stress is what? Offering a resistance. So you are not having any resistance means you are having a zero viscosity. Okay, that is what you are not having viscosity. So it is imaginary only. Any material, any fluid, if you are seeing, it have a some amount of resistance. It will be offering some amount of a resistance. So that is what ideal fluid is. It is only a imaginary fluid, and it is not existing in real. And it is what closer we can get to ideal conditions. Superfluid, some superfluid like cryogenic conditions like helium-3, helium-4, it can be assumed as an ideal fluid because it is nearly having an zero shear stress, but it's not absolute zero shear stress. A negligible amount of shear stress is there, so that can be considered in the case of an ideal fluid. And in case of real fluid, this is what a real. The fluid whichever possesses viscosity is what is said to be a real fluid. In real fluid only, we will be having these three: ideal plastic fluid, Newtonian fluid, and non-Newtonian fluid. So all the fluid, that is what a real fluid, we are having a lot of real fluid. Standard fluid we are seeing water as well as air, and so many fluids are there. Now we will see the remaining these three types of real fluids. So about a Newtonian fluids. So Newtonian fluids, the line itself you can see it have a linear relation. You are seeing a straight line. Okay, so a linear relation exists between velocity gradient and shear stress. So the proportionality, direct proportionality between shear stress as well as the rate of shear strain. Okay, that is what velocity gradient. That is what you will be saying as a Newtonian fluid. Example for Newtonian fluid is water, benzene, etc. is a example of Newtonian fluid. Similarly, for a non-Newtonian fluid, the real fluid in which the shear stress is not proportional to rate of shear strain. So that's what you can able to see as in a curve form. If it is directly proportional, then it will be a straight line. It is not directly proportional. That's what you are seeing as non-Newtonian fluid. The example is plaster and service. It is not having the direct correlation between shear stress and shear strain. And ideal plastic fluid is what it is. The shear stress is more than that of an yield value, and shear stress is proportional to rate of shear stress because you are seeing a linear line, but it is a more value and it is not starting from the zero. You can able to see initially from the zero velocity itself, it is having at instant, it is having some shear stress. That is what is called to be as an ideal plastic fluid. Example of that one is toothpaste that can be considered as an ideal plastic fluid. So now we will see few problems in problems on viscosity. So the velocity distribution is given in a plate as being 2 by 3 y minus y square. Which u is what the velocity in meter per second at a distance y meter above the plate. Determine the shear stress at y equal to 0 and y equal to 0.15 meter. Take the dynamic viscosity of fluid as 8.63 passes. So here it is given that u equal to 2 by 3 y minus y square, that is given in question. So from this you will be identifying what will be du by dy. Du by dy, that will be differentiation with respect to y. If you are differentiating with respect to y, the y if you are differentiating, that will be what, 2 by 3. Y square if you are differentiating, that will be what, 2y. Because we are knowing differentiation. So on the differentiation, anything x power n d by dx of x power n, if you are putting, that will be what, n into x power n minus 1. The power you are subtracting 1 and that power will be going on the prefix. By that way we will be calculating du by dy. And now du by dy at y equal to 0, because it is asked to identify at y equal to 0 as well as y equal to 0.15. So du by dy at y equal to 0 if you are putting, so here you are going to put the value as 0. So 2 by 3 minus 2 into 0. So this term will get 0. So the value is being 2 by 3. So the 2 by 3 while you are calculating, you are getting it as 0.667. So similarly, du by dy at y equal to 0.15, we are getting it as the value 2 by 3 minus 2 into 0.15, because 0.15 is what y value. So you are calculating it as 0.667 minus 0.30. So you are getting the value as 0.367. So now we got two values, 0.667 and 0.367. It is getting used on the continuation. So now mu value is given in the problem as 8.63 poise. So that is getting converted into Newton second per meter square. So 8.63 divided by 10 if you are putting, you will be getting into a Newton second per meter square, because poise if you are seeing, and poise to Newton per second per centimeter square if you are seeing, there will be a 10. So the 10 poise is what 1 Newton second per meter square. By that way, you can able to make dividing by 10, you can convert into poise to Newton second per meter square. So now we are knowing the correlation tau equal to mu into du by dy. So on this we are going to substitute the already calculated value of 0.667 for the y equal to 0. So by that you will be getting the value as 0.5756 Newton per meter square. Similarly for y equal to 15, 0.15, 0.15 meter. We are calculated the value earlier 0.367. That's what you are substituting, and we are identifying the value for a shear stress at y equal to 0.15 meter as 0.3167 Newton per meter square. We will continue with the next problem. So now the plate is given 0.025 mm distance from the fixed plates that moves with 60 centimeter per second. So the distance is given and the velocity is given and requires a force of 2 Newton per unit area. So per unit area is given, that is 2 Newton per meter square. So it is definitely it is a shear stress, because shear stress unit is what? Newton per meter square, even though they used the word force. So now it is required to determine the fluid viscosity. So this is what the given one. So the sketch also given in the question. So now in the solution you are seeing distance between plate is given in the question as 0.025 meter mm. So that we are converting into meter. We are knowing 1000 mm equal to 1 meter. So by that way you are making into 10 power minus 3 meter. So that is what 0.025 into 10 power minus 3 meter is what the given data. And you also it is given centimeter per second, but the standard unit is what? Meter per second. We are converting into meter per second. And force on upper plate, it is given F equal to 2 Newton per meter square, but it is not actually a force, it is a shear stress value, because force unit we are knowing it is being Newton. So what is given is the value of shear stress. So fluid viscosity we will be knowing tau equal to mu into du by dy, and we are having the change in velocity is what? 0.6 meter per second, and change in distance is 0.25025 into 10 power minus 3 meter, and tau value is given in the problem as 2 Newton per meter square, and tau value is given. So that what you are substituting here in the tau, and mu is what? That is the unknown one, and du is given as well as dy is given. Only unknown is what? Mu. So easily we can identify what is the mu value. So take the other things on the other side, okay, so that it is going to get multiplied here and it will come into the denominator. So make the calculation. So by calculation you are going to get what is the viscosity value, fluid viscosity value. So we are seeing Newton second per meter square, and we know 1 Newton second per meter square is what? Equal to 10 poise. So you are multiplying with 10 so that we are can able to convert into a poise. So the value, final value you are representing in case of an poise. And another problem. So in this problem the given data are area is given, the area value is being 1.5 into 10 power 6 mm square, converting into a meter square, because meter is what the standard unit in case of a linear unit. Similarly speed value is given, velocity is given directly in meter per second, and also the distance is given 0.15 mm. So you are converting into a meter. So mm is converted into meter, and the value of viscosity is given in poise. So poise to conversion into Newton square second per meter square, what you have to do? We know 10 poise is what? 1 Newton second per meter square. So 1 poise equal to this 10 will come to this side. So that will be what? 1 by 10 Newton second per meter square. So as the next thing, using the standard equation, tau equal to mu into du by dy. So that will be what? Mu is what? 1 by 10, and the du value is given in problem, and also dy is given. So directly we can able to identify what will be the required force. So tau value we can identify first. So from this we can identify the tau value. Now with the help of this shear force we can identify. So tau we will be knowing that is being what? Force divided by area. From that we can identify what will be the shear force. So shear force equal to calculated tau value into area. Acting area is what? 1.5 meter square. So that we identified what is the shear force. About the power required to move the plate is what? That is force into velocity. So we had already having a velocity 0.4 meter per second. So force into velocity is giving you about the power required to move the plate. And then the next problem. So here the given data are, it is given the shear of an oil having viscosity of an 1 poise. So poise we know it is being 1/10 Newton second per meter square, and if the data is given in centimeter means we have to convert into what, meter. And also the distance between shaft and journal bearing is given in mm, that also it is required to convert to a meter. And the speed value is given 150 rpm. Okay, so now as the speed value is given in rpm, we need to convert into a velocity of meter per second. There is a correlation between tangential speed of shaft, the u value, that is equal to pi dn by 60. By substituting that, we can be able to calculate what will be the linear velocity. This is a rotational velocity, we are converting into a linear velocity. So now we can make use of an equation, our viscosity equation, tau equal to mu into du by dy. So now we are having du value, that is being what, u minus 0, change in velocity between shaft and bearing. So that will be what, equal to 1/10. Okay, that is what it is given in problem itself, into du value is what we are having, u value. So u value is what, 0.785, as well as dy value is 1.5 into 10 power minus 3. So we can able to calculate the answer. And one more problem. So calculate the dynamic viscosity of an oil. So the lubrication between the square plate value is being 0.8 into 0.8. That's the size, and it have an inclination as shown in the figure, and weight of the square plate also given. And you will be having the thickness of oil film is being 1.5 mm, and you are required to calculate dynamic viscosity. This is the given data. Area is given 0.8 into 0.8. So you are making it meter square, and there is a theta value, and the weight of the plate is given, and the velocity is given. So now, with the help of the given data, now you are solving it. Thickness of the oil film, that is what it given in the sketch itself, that is being what, 1.5 mm. So that is getting converted into a meter. And also it is having an inclined plane. So on the inclined plane, we are going to make conversion into a normal plane. Okay, that is what you are making horizontally. So along the plane, how the force is acting. For that, if you are acting force, if you have to calculate, you have to make adjacent side mean you have to multiply the weight with that of a cos 60, because that is what on the adjacent side. So theta is here, and the theta will come here. So it will come on the adjacent side. So that is why W into cos 60 you will be putting, and W value it is given directly in question, so that you can identify along the plane what is the weight. That will be a 150 Newton by calculation. So now that weight is what you are going to consider. That 150 Newton force is what you are going to consider. So divided by the area is being what, 0.64 meter square that we calculated, so that you will be having a change in velocity, that is 0.3 meter per second. So dy value also it is known, 1.5 to 10 power minus 3, and then remaining substitution is easier. So tau value is what, that will be 150 divided by 0.64, and only unknown is what, mu. Remaining thing you had substituted, so that now you are calculating mu value as this 150 by 0.64, and this is going to the left side, means it is going to get reversed. That is what, 1.5 into 10 power minus 3 divided by 0.64 into 0.3. So by calculation, now you are getting it in Newton second per meter square. As you have to make for final presentation into poise, means you have to multiply it by 10. So you are multiplying it with 10, so that you can able to make your final representation as 11.7 poise. So thank you very much. We will see with the next video lecture. Okay.